Okay, so our next speaker is Sachin Vaidya, and I forgot the title of your talk.
I'll show
Okay, he's going to tell us the title. Sachin, of course, is from IISc Bangalore. And, oh yeah, this doesn't quite. Order and chaos in SU2 matrix model. So Sachin, please go ahead.
Okay, it's a great pleasure to be here for Balfest, and I'd like to thank all the organizers. We missed thanking Alok, so I think I should take an opportunity to thank Alok, who's one of the organizers. And the juicy details of my interaction with Bal will be on Thursday, but the short summary of what I'll say later is that it's an honor to have Bal as a teacher and a pleasure to have him as a friend. So what I want to tell you today is about some work on the SU2 matrix model. It's fortunate that Denjo talked about matrix models, so you will see some of the things that he talked about, a few of the things that he talked about. And although the title of the conference strongly emphasizes quantum, almost all of what I will tell you today is classical, and hopefully towards the end there will be a little bit of quantum in it. This is work done with my student Chaitanya Bhatt and a summer student from IIT Bombay, Vijay Nirmali, who's now at Cambridge. Okay, so this is the plan of my talk. I will introduce the matrix model and show you that in some particular singular value like coordinates, the matrix model has a very nice description. And in particular, there is an emergent tetrahedral symmetry, which may be related to the kind of symmetry Denjo briefly mentioned, but we'll have to wait to see if it is. But what I will do is then look for classical orbits, and these classical orbits can be classified by subgroups of this tetrahedral symmetry. So we will study their stability. And as you increase the nonlinearity, because this is fundamentally a nonlinear classical system, these orbits destabilize, and they destabilize in a most interesting way. So I will use three tools to study the destabilization. One is called the Monotomy Matrix, which I'll tell you a little bit about in case since maybe not all of us know about it. I found out about the Monotomy Matrix only a few months ago. I'll also, the other tool that we will use to study the destabilization is Lipunov exponents. And finally, the tool which I discovered only recently, which I found out about only recently, but is apparently a hot topic in condensed matter, in parts of the condensed matter community, which is called small system thermodynamics. So these are three overlapping tools that we will use, and it's very satisfying to see that they all point to the same. They all converge to the same conclusion. And one interesting point about one of the interesting points about what we learn is about ergodicity breaking that takes place when the systems become chaotic, and the connection to, and I will make some conjectures about the connection of this ergodicity breaking to possible phases of this system. So that's what it is about. Okay, so let me start. The SU2 matrix model is very easy to describe. Denjo started off that description, but I will tell you anyway. The basic building block is a 3x3 real matrix, and it has rotational degrees, physical rotations act on it. Here I have included in physical rotations also the parity, which is why it's O3. And there are gauge rotations. So physical rotations act from the left, gauge rotations act from the right. And in terms of this matrix M, we can define an electric field, which is just M dot, and the magnetic field, which is linear in M and quadratic in M. So there is a certain history behind why the magnetic field is defined like this. A short, if you have a telegraphic answer to that, is that this magnetic field is nothing but the pullback of the Maurer-Cartan form to an underlying S3 on which the matrix model has been constructed. But given the electric and magnetic field, we can go ahead and write down the Lagrangian, which is just E squared minus B squared, and I've put in a 1 by 2 G squared, which is the Yang-Mills coupling. And with Amilcar Quiros, Barr and I looked at this model. At that time, we were interested in this model because we were interested in the statistical properties of colored states. But it turns out that his model is quite versatile. And if there's time, I can tell you what other interesting things you can do with this model. But one thing you notice immediately is that this is just quantum mechanics, or this is a model with finite number of degrees of freedom. And the potential V that I've written here is the square of B. So it has up to quartic terms, quadratic, cubic, and quartic. And so you immediately recognize that this model that I've written down is just a multi-dimensional quartic oscillator. Okay. But we can do more if we choose the right coordinates. This, of course, we know that you can always do more with the right coordinates. So in particular, if you decompose the matrix into SVD-like coordinates, that is, you choose an R on the left and an S on the right correctly, then you can write this as R times a diagonal matrix times S transpose. You can do this for any 3 by 3 matrix. And with R inverse R dot and S inverse S dot defined like this, these are essentially angular velocities. The Lagrangian has a fairly simple form. And because this matrix is because the rotations from the right are gauged, we would like to set lambda to 0. So in order to concentrate on gauge invariant dynamics. Right? So in particular, we will set lambda to be 0, and for the things that I want to tell you today, we will also look at the spin 0 sector. We will also set omega to 0. So we have gauge invariant spin 0 dynamics that we would like to look at. So if you put this ansatz M equal to R A S transpose into the formula for the potential which I had shown you earlier, then like I said, this is basically a quartic oscillator. So you can see quadratic, cubic, and quartic terms. But it's more than but there's more to it than this. There is, of course, a symmetry. For example, you can exchange any of the A's, and you can flip two signs, like A1 goes to minus A1, A2 goes to minus A2, for instance. So there is an action of S3, then there is this action of Z2 cross Z2, and it comes together very nicely as a group that is isomorphic to the tetrahedral group. So this potential has a tetrahedral symmetry in the variables A1, A2, A3. This we could not have seen unless we had gone to these singular value coordinates, and it turns out that this tetrahedral symmetry will play a very important role in understanding both the dynamics as well as chaos properties of this model. And if you then include time reversal, then the full symmetry of the Hamiltonian is this tetrahedral symmetry times a Z2, which is the time reversal symmetry. So this is what this tetrahedral symmetry. This is a picture of what this tetrahedral symmetry looks like. So I've plotted equipotential surfaces. So if the potential is very small, 0.05, then the equipotential surface is actually made up of 5 disconnected blobs, and you can see the tetrahedral symmetry quite obviously. At a critical value, 3 by 32, the blobs connect up. So this critical value is actually the saddle point of the potential. And then you push it further, the blob just grows, and then this is sort of a generic picture at some very high value of the energy. But in any case, this is to show you what the tetrahedral symmetry looks like. Okay. And so if I go back from that Lagrangian, if I go back and go back to that Lagrangian, construct the Hamiltonian, then this in the spin zero, color zero sector, this is the form of the Hamiltonian. And about 18 or 20 years ago, these people identified this Hamiltonian, almost exactly this Hamiltonian, as a three-dimensional generalization of the well-known Henon-Hiles problem. So the problem of the SU2 gauge matrix model in this particular sector is exactly the three-dimensional Henon-Hiles problem, and this should tell us, for those of us who know anything about Henon-Hiles, this should prep us to interesting things that will that we will discover. Okay. So like I said, the disconnected pieces connect up when at some critical energy. That's the saddle of V. So I'm going to rescale my A's and P's and then work in terms of this dimensionless Hamiltonian, where my epsilon is G times e to the half. And the advantage of working with this rescaled Hamiltonian or this dimensionless Hamiltonian is that this epsilon measures nonlinearity. So for example, if when epsilon is 0, this term and this term drop off, and this is nothing but the three-dimensional isotropic oscillator. And we know that the three-dimensional isotropic oscillator has only closed orbits. Yeah. Yeah. So that's why I was careful to say SVD like. And this has to do, it is a small but an important technical point, but it is a technical point. So if it's okay, I will come back to it at the end. So, but the short answer to your question is that in the way that I have done the decomposition, A's take all possible real values, not just positive values. Now, a long time ago, this mathematician Weinstein showed that if you have closed orbits, then for small nonlinearity, the closed orbits continue to exist, and these are called nonlinear normal modes. For this particular system, this three-dimensional Henon-Hiles system, people have been, mathematicians, especially those who work in dynamical systems theory, have been looking at this particular problem for a while now. So these people, Montaldi, Roberts, and Stewart, they studied and organized these nonlinear normal modes for the problem that we are looking at. And they found that they can be organized like this, essentially by the stabilizers of, by the conjugacy class of the stabilizer of the orbit. So there are these 5 classes, and these are their names, A3, A4, A3, A2, B3, B4. These are just particular subgroups of TD cross T. And one way to think about these stabilizers is they are essentially symmetries of the initial conditions. So we have 3 A's, we have to specify 3 A's and 3 P's, and some of them may be equal to each other, or some may be one may be a particularly chosen multiple of the other, and that is a sense in which these subgroups are symmetries of the initial conditions. Okay. So what we are going to do is we are going to study perturbations about each type of the orbit. So I showed you that there are these 6 types of orbits. We are going to look at perturbations about each type of orbits. And generically, as you increase epsilon, these orbits destabilize when the perturbation becomes sufficiently large. So like I said, we are going to use 3 tools to study chaos. One is this Monotomy Matrix. The other is to computation of Lipunov exponents. And finally, some thermodynamic considerations. So I am going to focus on A4 and A3 because these have the most interesting and dramatic behavior. The other ones are interesting, but these are much more interesting. So I want to tell you only about A3 and A4 orbits. So A3 and A4 orbits, these correspond to straight line orbits. In fact, like I said, they destabilize in a most interesting way. So I will show you what happens for A3 and A4. Now, in dynamical systems theory, people routinely use this technology called the Monotomy Matrix, which is that you start off with some periodic solution, look at a perturbation, and look at the equation, time evolution equation of this perturbation. So that's typically of this form. X, of course, is not just the coordinate, it's a column vector of the coordinates and the momenta. Now you can, once you have an equation like this, time evolution equation, you can then write down a time evolution operator or a time evolution matrix U, which will map x of 0 to some later time x of t. And if you evaluate U for at the end of the time, at the end of the time period, or for the time period t, then U of capital T is called the monotomy matrix. And eigenvalues of U carry information about the stability or instability of this monotomy matrix. So because U is real, for instance, because U is real, the eigenvalues come in complex conjugate pairs, and an orbit is unstable if and only if one or more eigenvalue lies outside the unit circle in the complex plane. Now, for both A3 and A4, the orbits are themselves known analytically. A3 is harmonic function and A4 is an elliptic function. So we can actually do a lot of the work that people are forced to do numerically. A large amount of it we can actually do analytically, and we can gain insight in the question of stability of these orbits. And in particular, for our situation, it's enough to study this quantity gamma, which is trace U minus 2 by 2, some function of trace of U. Okay. So let me tell you what happens for the A4 orbits. So this is the initial condition that characterizes the A4 orbit. And if you look at if you do that perturbation around it, etc., the perturbation organizes itself into this, the perturbation equation, fluctuation equation organizes itself into a Whittaker-Hill equation. And this is what the Whittaker-Hill equation looks like. But one thing you notice is that it's nothing but the Schrodinger equation for a particle in a periodic potential. And these etas, alphas, and betas, these are constants that depend on A, which is my initial condition, which itself remembers the initial total energy. So the energies, so we know that for a particle in a periodic potential, even without doing any calculation, you know that there should generically be bands and band gaps. They play them, but because they are functions of A, it plays itself out in a rather interesting way. So when you have, so this eta, which is a constant that depends on A, when eta is an allowed region in the sense of a periodic Schrodinger problem, then the corresponding solution is a block wave function, and that corresponds to a stable perturbation. And when eta is not in the allowed band, then what you get is a non-normalizable solution to this equation. So that means that for this classical mechanical system, this is a perturbation that grows exponentially in time. So here, numerically, what we saw is that when energy g squared E is less than 3 by 2, then the orbit, A4 orbit, is always unstable. And then for energy greater than 3 by 2, we find repetitions of, we find repeated bands of stable and unstable regions. So this is what the monotomy matrix, the gamma looks like. So I've plotted gamma as a function of energy. For low values of energy, the gamma is greater than 2. And so it's unstable, and then it becomes stable at around at about 3 by 2, and between, in this small region, it's stable, and then it again becomes unstable, and it's stable again, and then it's unstable for a tiny region here, then again stable here, etc., etc. So there's a repetition of stable and unstable region, and it goes on and on. It just goes on and on. Here I've plotted it till energy equal to 100. And this is what it looks like if you actually plot the orbits. So this is near 3 by 2, where there was there was a jump from stability to instability. So if you plot the orbit in the A1, A2, A3 space for 4.999, then the orbit looks like a hairball. But if you plot it for 1.501, which is just above 1.5, then it's a straight line. And you can check that this is what happens at every place where there is a transition. So we'll have more to say about A3 and A4 orbits, but let me tell you about the monotomy matrix for the A3 orbits. So again, the idea is very similar. I'll go through this a bit quickly. So these are the initial conditions now that describe A3 orbits. You can solve for the actual orbit. Again, you can solve, but now it is an elliptic function. So you again look for the perturbations, etc., etc. So again, you get a Schrodinger equation, but for a particle in a periodic potential, because this potential is a more complicated one, because the starting point was an elliptic function rather than an ordinary harmonic function. But again, we have bands and band gaps. And here we find that for energies less than the critical energy, that is at that saddle point, for energies less than the saddle point energy, our gamma oscillates between plus and minus 2 with ever increasing frequency. And these peak spacings, so the places where it destabilizes or becomes stable again, these peak spacings, they vary geometrically as we approach the critical energy from below. And the same thing happens for energies greater than EC. So again, there is an oscillation, but now with ever decreasing frequency. And the peak spacings again vary geometrically as you approach the critical energy from above. So this is what the picture looks like. So I've plotted the energies for the subcritical region. And one thing, so this is from 0 to 0.9. Then I've taken a small region here and blown it up. And then again taken a very small region here and blown it up, and so on. And I've done the same for the supercritical part. So this is from 0.09 to 0.093 to 0.09377. Then I've taken a small region here and blown it up. Well, you get the picture. But so one thing you immediately notice is that there is a self-similar behavior. And so this is if you like the stable to unstable flip for A3. So if you look at this region, I think I have taken it near 0.3 up. Well, it's one of these regions, I think. 0.3. So I've looked at this region. I've looked at this point here. And you can see that it's a transition from a stable to an unstable one. And so you get a straight line for some energy, and for some energy slightly greater, again, it just looks like a hairball. And you can, because it's a geometric function, you can compute the ratios of these hairbands. They are not the same on either side. We get these two incredible numbers. I call them incredible because I've never seen such numbers before. I think they are quite pretty. But what is interesting and important is that we get two different geometric constants on the two different sides. Okay, now let me quickly tell you about the Lipunov exponents. So again, you can compute the Lipunov exponents. So we compute the Lipunov exponents orbit by orbit. So these are the Lipunov exponents for the A3 type of orbits. So here again you see that the Lipunov exponents are non-zero, then they become zero. Then they are non-zero, they become zero, non-zero. And these alternation between non-zero and non-zero coincides exactly with what I showed you earlier about the monotomy matrix. So these are completely consistent with the results from the monotomy matrix. And we can try to fit this curve to we can try to fit it, and it turns out that the growth is like e to the 1/4 for large E. you can do the Lipunov exponent calculation for A3 as well. Again, A3 of course for high energies, the bands are very, very widely spaced. So we can see only one band here. But again, the energy goes like e to the 1/4. And because the bands are very widely spaced, I'm not able to plot the next band here. But you can then go ahead and look at generic perturbations, and for generic perturbations also, you can see that the plot of Lipunov exponents versus e to the 1/4 is a straight line. And this was a result that was, I think, first discovered in a very closely related model by Hashimoto, Murata, and Yoshida a few years ago, where they found that the Lipunov exponents grow like e to the 1/4. Okay. So the third point so I told you about the monotomy matrix, the Lipunov exponents, and now about these small system thermodynamics. And the idea basically comes from the observation that for arbitrary initial conditions, our system is chaotic, and chaotic systems are also ergodic. So by an old theorem of Birkhoff and Khinchin, for ergodic systems, time average is the same as ensemble average, which, if you like, is one of the foundational principles of the way we do statistical mechanics. So if this is true for an ergodic, for a chaotic system, then the question is, can we adapt thermodynamic ideas to describe this chaotic system, even though it's a system with just 6-dimensional phase space? And this idea was suggested many years ago by this mathematical physicist Berdyshevsky. And the starting point is actually goes back to Gibbs. So Gibbs says that if you compute the volume of phase space less than or equal to an energy E, then you can define entropy as just the logarithm of this volume. And then you can define the Gibbs temperature as or 1 over the Gibbs temperature as just the derivative of S with respect to E. But for ergodic systems, we have another definition of temperature through the equipartition theorem, which is that the temperature is the time average of P times del H del P. For each P, this is not a sum over P. For each I, this is not a sum over I. So there's actually many equations. And we checked numerically that we computed the Gibbs temperature and computed expectation value of P1 squared, P2 squared, and P3 squared. You can see that for low energies there are small deviations, but for higher energies the ergodic values coincide completely with the Gibbs temperature. So we can say that the system has thermalized. And A3 and A4, the orbits that I talked about, these are special because because of the presence of those bands and band gaps, these orbits actually break ergodicity. So you can, for A3 and A4, you can compute the Gibbs temperature and these ergodicity averages, and you can see that there are regions where they don't match. So this is for A3 and this is for A4, and these are exactly the places where you have those band gaps. So ergodicity is broken exactly in the, so this actually coincides completely, confirms fully the calculation from the monotomy matrix and from the Lipunov exponents. So it's broken exactly in the regions where the Lipunov exponent vanishes. And so this suggests to us that ergodicity breaking may have a thermodynamic interpretation. So this is where it becomes a little bit conjectural, but I think that we have reasonable evidence for this. So for A4 and A3, the stable orbits exist for arbitrarily high energies as long as the energies are in the bands. And if you are in the right band, then these trajectories don't explore the entire available phase space. In particular, they are confined to certain corners. So these trajectories, they clearly break ergodicity. And numerically, we have found that the equipartition theorem does not hold. So The question is whether we can interpret ergodicity breaking as phases, because it seems to us that at least from the thermodynamic discussion, such a conjecture is not unreasonable. And it's not unreasonable, it is interesting and attractive to have such an interpretation, because we know that in gauge theories, there are phases that go by the name of colored glass. There are glassy phases. So it would be interesting to see whether the phases that come here from ergodicity breaking are related to glasses. Now, there are two corners of, there are at least two corners, one for A3 and one for A4 of the configuration space, from which the dynamics doesn't break out. It gets stuck in these corners. So what I want to show you is some version of a Poincare section. So this arrowhead, if you like, is a particular way of representing the configuration space, and I don't have too much time to go into that, but it's a particular way of representing the configuration space. And if I take the A4 orbit, for an energy where it is ergodic, the orbit spreads over the entire arrowhead. Whereas if I take the A4 orbit at a nearby energy which is in the band, then the orbit is stuck at the top tip. It's just stuck there. And you can say it's the same statement you can make for, it's the same thing for A3, except that for the A3 orbit, when you choose the energy in the energy band, is stuck at the two tips, this tip and this tip. So it can go from, it can be at either of these tips, but it cannot be anywhere else. Okay, and so finally, because quantum is part of this title of this thing, I thought that I should say that the quantum SU2 matrix model with one flavor quark, we studied it some time ago with my student Mahul Pandey. And at that time, we found that quarks get stuck in special corners of the space of gauge fields. And in particular, we found one quantum phase where the quarks got stuck to gauge fields corresponding to this tip. And like I just showed you, the classical theory shows that A4 orbits, if they have the right energy, get stuck there. We found another phase which is actually a color spin locked phase, and for that phase the quarks get stuck either at this tip or at this tip, at gauge field configurations corresponding to either this or this tip. And again I showed you that these correspond to A3 orbits with the right energy, classically. So I think I have just a minute or two left, so I'd like to end now. And yeah, I know what I wrote behind, so I can read it off from memory. So the question of what quantum signatures of chaotic dynamics is, of course, not settled. There are many answers to it, each one both attractive as well as with its own drawbacks, and there is no simple answer. But we would like to muddy the question further by adding that classical ergodicity breaking is what signals quantum phases as one of the oh, is there something I can do? I should do? Unmute. Oh, thank you. So to this list of connections between of the signature of quantum signature of classical chaos, we would like to, like I said, add one more piece. Okay. And I will just leave the summary for you to look at. I won't read it out, except one point that which I didn't have time to talk about, is that one of the orbits actually destabilizes via the same mechanism that Feigenbaum found, which today I do not have time to show you. So, so I will end with Happy Birthday, Bal.
The tetrahedral symmetry is only in the sector which is chosen, right? It is not in other sectors.
No,
it's not the global.
No,
for all the.
the tetrahedral symmetry is a symmetry of the potential.
Right.
So the symmetry will be there even when you move to sectors which have non-zero spin. So we are going to look at it about what happens when you turn the spin on.
Okay. The second question is, usually there is a problem between classical chaos and when you go to the quantum level.
Yes.
The transition.
Yes.
There is no quantum chaos.
Yes.
So can you tell something about it?
Yeah. So like I said here, there is no simple answer to what is the quantum signature of classical chaos. There are many suggestions, but each suggestion has some merits as well as drawbacks. All I can say at the moment is that we have only muddied the water more by suggesting that classical ergodicity breaking can actually correspond to quantum phases.
Okay, I'm going to take the question from online first and then I'll come back to you.
So there's a question from Professor Weigel. It says, nice talk, Sachin.
Hi.
The figure with the Lipunov exponents had some isolated entries. Do they have a certain interpretation?
Yeah.
Or it's just a matter of discretization?
Yeah, let me show that figure and I will, this one, right? Is it this figure that you had in mind? So these are these the isolated points that you were thinking about? But I assume that they are, and these are actually numeric artifact of our numerics. So in principle, there should be if there exists an analytic calculation of Lipunov exponents, and I haven't really seen one, they should be sharp.
Okay. Well, Kumar had a question first, and then I'll come back to them.
Your system was almost thermal, right? You showed.
Yeah.
So there was a good agreement. Right.
Yeah.
So what was the nature of the perturbation when this happened?
So this is for a generic orbit with generic perturbation. So it's a 6-dimensional phase space. You solve the equation of motion numerically, and then you make a you have the freedom to perturb all the 6 variables. So those are we are looking at the most general perturbation, and that is for those kinds of perturbations, we look at you look at an ensemble of orbits.
So if you, in this situation, if you play with the perturbations, I mean, if you make it bigger, smaller, or various things, when does this behavior start to depart from thermalization?
So if you make a generic perturbation, you miss ergodicity breaking. This is why group theory has turned out to be in fact, we arrived at pictures like this fairly early on in the game, and it's only after we discovered the work of Montaldi, Roberts, and Stewart that we realized that group theory provides us with a much more subtle tool. So if you use group theory to study orbits, then for A3 and A4 and for other orbits too, you make a full 6-dimensional perturbation, but for A4. It turns out that the orbit is stable. So even if the perturbation is 6-dimensional, the orbit continues to be a straight line, provided you have chosen the energy to be in the stable band. So then that is the situation which we describe as ergodicity breaking, because even the most general perturbation can't knock the orbit off.
So even the most general perturbation would show this thermalization behavior.
Most general perturbation will show this thermalization behavior, yes. And then for A3 and A4, this is what you will see.
Okay, thanks.
For the most general perturbation for A3 or A4.
Okay. Then Joe?
Your system, as I understand it, is one of 3 vectors in 3-dimensional space. And I think your A1, A2, and A3 are the lengths of the 3 vectors. Your potential involves the...
That's right. I don't want to call them vectors. Let me call them variables, because they do not transform
If you think of them, I mean, as the matrix says, your 3 by 3 matrix is really.
These are the 3 singular values. These are, if you like, roughly speaking, these are the 3 singular values.
I think they have to be the links of the 3 matrices.
What do you mean by lengths of
links of the 3 vectors? Because a 2 by 2 matrix is you have an SU2 Yang-Mills.
Yes,
which
this
means
is
that you started out with 3 2 by 2 matrices.
Yes,
which is equivalent to 3 vectors in 3-dimensional space.
Yes,
and those vectors are. I think you've restricted
the set of all possible 3 vectors in 3-dimensional space.
3-dimensional space, yes. But you're not allowing them to rotate. You've chosen angular momentum 0.
Yeah, we have chosen angular.
So there's no overall rotation. So you just have the oscillations of the 3 vectors, and I think one of them you had them 3 of them aligned. Was it your A?
Maybe you want to see the Hamiltonian?
Well, I remember the Hamiltonian.
Okay, what is there a particular graph or equation you want to see?
Your different sector. I think that the 3 vectors are aligned, and you're doing some perturbations about them.
This one? Are you talking about this?
Yeah, you had one of them which only A1.
Okay.
Sorry. Oh no, that was the one.
This one? Well, tell me your question and I will find the right slide.
my question is, can I visualize what is it? Can you visualize what's going on with the different ergodic systems in terms of the 3 vectors? Because I can orient one of the vectors to them pointing north, and then I have just 2 vectors rotating around, but they're not rotating; they're just oscillating. I
suppose so. I haven't thought about it like that. Yeah. I'm sure that it'll teach us something.
Is that a follow-up to Dennis' question?
Yeah, okay.
So you have to, A4 is a particular finite dimensional group. So, no. This the label A4 is not supposed to mean alternating group. I'm sorry that the people who came before me chose these names. I would not have chosen A4.
I see.
So
that is
it's not an A4 is this guy.
It's a D2 cross something, right?
Yeah,
Tetrahedral symmetry, the table which you showed.
I'll show you.
Yeah. So this is the.
This is
How do you also see that the number of orbits is 3 for such a breaking? Do you see it? Or
the three so you can choose the capital A that I had chosen. You can choose it in the first slot, or the second slot, or the third slot.
Okay, so that way. That initial condition is not specific. You could have A 0 0 or 0 A 0.
But under tetrahedral symmetry, you can go from one.
I don't know how these things connect to quantum system. But if you take, for example, the 2 torus, okay, in the 2 torus, if you one can write down a self-adjoint operator which evolves on the 2 torus, but the direction of the evolution on the 2 torus is an orbit which is not periodic, so it becomes ergodic on the 2 torus.
Yes.
So that is that will be good. However, this is but there is no fixed point here.
Yes.
Because it's a unitary evolution. So there are fixed points because there are stable orbits. You just have to change the time evolution from this ergodic orbit. You have to change some parameters. It will get fixed, but then it will again get fixed because of unitarity. But how do I go from one to the other? For example, can I say the stable orbit is stable? Can I make a perturbation? What issue? How do I make the perturbation? Okay? Unitary perturbations will do nothing. Okay? It seems that the appropriate quantum situation is a POVM, that is positive operator valued measure. If you do that, it appears that such orbits can get perturbed, and it may be stable, unstable, and probably one can classify the whole Tom class in this situation. It seems. Now, I want to make the final remark that I don't know how this ergodicity reflects in quantum system, but I'm sure that in QCD, the super selection sectors which you mentioned, for an appropriate chemical potential in the QCD Hamiltonian, the action on the super selection sectors or this unitary Hamiltonian is ergodic, and there are fixed points also, and it appears that they definitely have measurable consequences, which one can outline. It is not that because these are infrared effects, you see nothing. That is not true. Okay? There are actual experimental effects. Now it appears that in this context, even let's say POVM, one can then study these orbits in terms of your phase transitions. The POVM will test whether a particular stable orbit, stable point is in fact stable under the POVM.
Okay.
I suspect that these two things look very similar, but not exactly.
Okay. I think this requires more discussion. I think Sujay had a question. No.
Okay, then let's thank Sachin one more time, and we'll close the session for the morning.